extension number 4 in chapter 4, where we're going to talk about properties of linear relations. Now, the first thing I'd like you to do is work with a partner, and you might not have a partner, so work by yourself if you're doing it on your own. You can't even read that, can you? I think I need a partner to write down these things. Anyways, try this experiment, okay? Part A, you can put your answers here in the chart. Part B, then answer the question here, and then part C, graph the table. And I want you to try this on your own first, and you know my regular thing. I say press pause, and then you try it, complete it, then come back and double check your answer with mine. Alright, so press pause. First one here, 1 by 2, right? 2 by 3, 3 by 4, 4 by 5. Nice. Guess I've already extended. It'd be 5 by 6. And the next one after that would be, 6 by 7. So looking at the areas, 2 times 3 is 6, 3 times 4 is 12, 4 times 5 is 20, 30, 42, and so on, of course. Perimeter of rectangle number 1. 1 plus 2 is 3 times 2 is 6. 2 plus 3 is 5 times 2 is 10. 3 plus 4 is 7 times 2 is 14. And then hopefully you can see the pattern, 18, 22, and also 26. Now here's the interesting question. Which table of values represents a linear relation, and how do you actually know? Now notice that when I did this chart, the width of the rectangle always went up by 1 every single time, right? Plus 1, plus 1. Same thing over here, right? Always plus 1. Notice though, the area, from the first set to the second set, it went up by 4, then it went up by 6, then it went up by 8, then it went up by 10, and 12, okay. And then over here, it went up by 4, and 4, and 4. So interestingly enough, that the area, the change seemed to get bigger and bigger and bigger as the change in the width of the rectangle stayed at 1. Yet for the perimeter, the change was the same as the width of the rectangle changed by 1. So if you had to ask yourself which one do you think is a linear relation, I hope you said the perimeter. Okay, and why? I'll say the difference in the perimeter number was the same for each similar change in the width of the rectangle. Okay, right? These all went up by 1, those went up all by 4. Always the same. Okay, now let's see if we can graph the data in each of the table values, and then hopefully we can visually see which one represents a linear relation. Here we go. We'll do area, width. I guess I will do what, I'll try to space this out. 1, 2, 3, 4, 5, 6. And then it goes to 2 to 42. Wow. So, 2, 4, 6, 8, 10. Is that enough? 2, 4, 6, 8, 10, 20. That might be a problem. I don't think I get to 42. But maybe that's okay. 2, 4, 6, 8, 10, 30. I'll say. Well, let's see what we can do. The width of the rectangle is 1. The area was 2. That's here. 2 then became 6. 2, 4, 6. 3 then became 12, I believe. 12. 4 became 20. 5 became 30. And I hope you can kind of see that we don't actually have a straight line here, but we have some sort of curvy, it gets steeper and steeper. Okay? Now I know I'm not supposed to actually connect the dots together, but I just want to show you that trend. So that of course was area, so probably not a linear relation. And that hopefully is good news, because then it confirms the answer in part B, that perhaps the perimeter will be the one that is a linear relation. So let's do the same thing. 1, 2, 3, 4, 5, and 6. I hope you did this in your notes. I'll use the same scale, 10, 20, and 30. And you plot the values, so 1 and 6, 2 and 10, 3 and 14, 4 and 18, 5 and 22. I see this already. Looking good, right? Straight. So, answer for part C, yes, also perimeter. That's very good that our answers confirm each other. Why, once again, how do you know? Well, hopefully you can see that the points actually lie on a straight line. The points lie on a straight line. And if you were to go back to your answer in part B about that change is similar, here's what I was actually saying. Look, if I went 1 in increase in the width, the perimeter went up by 4. And it's the same here, right? Going 1, go up by 4. Yeah. 1 up by 4, right? It's always the same. Where here it wasn't. Because 1 up by what? 4. 1 up by 6. 1 up by 8. Not the same. Okay? So, notice we have two ways now, looking at a table of values or looking at a graph to show if something is linear. So now let's go ahead and try to apply some of this stuff, okay? It says, number 1, determine whether the following equations represent a linear relation. You can make a table of values or use a graph to support your answer, okay? So, it's up to you what you want to do. I gave you some graph paper here. I kind of like using a table of values first, to be honest. So if I did something like this, 0, 1, 2, 3, I went up by 1. I'm hoping to see that on the y values, the corresponding difference is also the same when I change from one x value to the next. So if I plug in 0, 2 times 0, 0, minus 1 is negative 1. 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. Notice here, as I increase by 1 in the x, the y seems to be increasing by 2 every single time. So what do you think? Yeah, I definitely think so. Yes, this is linear. Okay. Now, you could graph this out as well. I will do that for this one. Let me just quickly draw. Oops, not so nice. Try and do it freehand. X, Y, and for part A, 0, negative 1, 1, comma 1, 2, comma 3, 3, comma 5. Hopefully you can see, yes, it's on a line. Okay. Now how about y equals to 2? Well, y equals to 2, that's here, right? But that's not the only place where y equals to 2. It's also here, and also here, and also here, 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 here. Notice it's pretty much every point on this horizontal line. So is this linear? Yes, it is. It's a horizontal line. So even though there was no change in y with every change in x, it's still constant. The change is constant. Okay? Now x plus 3 is interesting, because if I were to solve this, I get x equal to negative 3. Hopefully, remember from Math 9, this is that's right, a vertical line at x equal to 3. So, is this a linear relation? Yes, also a linear relation, because this is a vertical line. Alright, Ooh, D and E. Got two more. Maybe I'll use the grad or the grid underneath now for D and E. Okay. X and Y. What's this bar symbol? If you don't know, it's actually called the absolute value. What happens is it takes every negative value and changes it into a positive value. So the absolute value of -2, if I plug it in like this, that actually becomes +2. So there's my Y value. -1, the absolute value becomes +1. The absolute value of 0, just 0. What happens with a value that's already positive? Well, it just stays there. It doesn't change. So if I were to graph this out, hopefully you can see that it is oh wait, so strange. It's like a V-shaped graph here. So once again, is this linear? Well, parts of it is, but on a whole, is it? Well, look, you're subtracting one here, and then all of a sudden you're adding one. So is it the same throughout? Sorry, not linear then. Okay. And finally, the last one, I think you should do the same thing. Let's make a table of values. I'll use the same values, -2, -1, 0, 1, and 2. This time -2 squared is 4. 4 plus 1 is 5. I'm making the table of values. -1 squared is 1. 1 plus 1 is 2. 1, 2, and 5. And if I were to plot these lovely points, interesting, what do I get? You get this U-shaped graph, which I told you earlier in a previous video was called that's right, a parabola. And that definitely does not look like a line. So, nope, not linear. Okay. A few more here. Oh, one more. What about this idea? A rectangle has a perimeter of 30. And the length is related to the width somehow. So think about a rectangle. I have a length and a width. The perimeter is equal to 30. So twice of the length plus twice of the width equal to 30. And if I ask you to solve for like length or width, I guess I can say 2L equals to 30 minus 2W. Or L equals to, we'll divide every single term by 2. You get this lovely equation. And if I made a table of values here, not X and Y this time, it would be perhaps W and L. Hopefully if W was 0, notice L is 15, 1, 14, 2, 13, and so on. Hopefully you'll see that yes, this is also linear, yes. And if you were to actually graph out this line, I'll do it over here like this. Man, I need to draw a better freehand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Anyways, it'll be 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Hopefully you'll see a line that looks like this. And definitely, that must be linear. Once again, here was the table of values. Adding 1 on the width every single time, subtracting 1 on the length every single time. Cool. Linear. Alright, well, here's another example of what a linear equation could be. Tickets for the Burnaby South Christmas School Dance. Probably not happening this year with COVID, but hey, you never know. They cost $20 each, but the rental of the school gym, decorations and food, yes, food cost $1,000. Now the gym holds a maximum of 500 people, so here's the situation. Can you create an equation that relates the number of tickets sold to profit? Now profit is not just the amount of money you bring in. Profit is actually the amount of money you bring in, which is called the revenue minus the cost, right? So before I create an equation, what is the independent variable? What is the dependent variable? What can you control? What can't you control? Well, the independent variable probably is the number of tickets, right? Number of tickets. That, my friends, well, it's a variable. What depends on that? Well, the profit, right? Because there is a certain amount that you're going to make for each ticket sold, but there's also costs involved. So really, I'm asking you to find an equation that relates profit with cost. What is profit again? I told you, it's revenue minus cost. How do I find the revenue? Well, that depends on how many tickets are sold, right? So what is the price of each ticket? 20. So 20, how many tickets are sold? I don't know. I guess we'll call it T. It's a variable, right? What are my costs? No matter what happens, no matter if I sell 0 tickets, I still have a cost of $1,000. So I have to subtract 1,000 off my revenue amount. And that equals to profit. So this is the equation that describes this situation. Now, if I ask you for the domain of course is the independent variable, that's the T. How many tickets can you sell? Well, the lowest, that's right, 0. That's pretty sad. The highest, well, there's a maximum of 500 people, so you can't sell more than 500 tickets, because then you'd be in trouble with, like, the fire department. Or, of course, the number of tickets is a whole number. Now, the interesting thing is now, what about the range? So, looking at the lowest amount of tickets sold, 0. What happens to be your profit? Well, that happens to be negative 1,000. So that's probably the lowest your profit could be. And what about the largest it could be? Well, if you sell out, 500 tickets are sold. You plug that into the equation now. 20 times 500 is what? 10,000 minus 1,000. You could make a whopping $9,000. Whoa! Notice, however, in this case, P must be an element as a multiple of 20, because each ticket is worth $20. Okay. So knowing this, I'm going to ask you to graph out the equation. All right. So let me do my axes. This time I'm not going to put the X way down there. I'm going to move it up just a slight tad. And the reason why I'm doing that is because I see that there's a negative value, right? So maybe I'll say this is negative 1,000, 1,000, 2, 3, 4, 5. Oh, I'm not going to fit this. Okay, maybe each one of these is 1,000 then. So negative 1,000, 1,000, 2,000, 3,000, 4,000, 5,000, 6, 7, 8, 9, 10,000. That's probably better. That's my profit. Here are my number of tickets sold. And I guess I can go from 100, 200, 300, 400, 500. The hard part sometimes with graphing is actually the scale to make sure it fits. Okay, and then I think if we continue to do this, I can plot the point. No tickets sold, lose $1,000. All my tickets sold, $9,000. Woohoo! And you could have things in between by just putting some random numbers. I can plug in like 100. 20 times 100 is 2,000 minus 1,000 is 1,000. So at, let's say, 100 tickets, I'd probably be here. And then I can just plug in other numbers like 200, that's 4,000, 3,000. Hopefully you can see that I get something like this. And if I connect them together, right, I get a line. Now, here's a new term. And I want to introduce this to you now. What is the rate of change in this situation? What does that mean? Rate of change. It means how does the profit change as the number of tickets change? Well, if I sell one extra ticket, how much more money do I make? That's right, $20. So really my rate of change here is $20 per ticket. What I'm saying is for each additional ticket sold, the profit will increase by 20. It's really that table where we're looking at how one variable changes compared to another. Now, on a graph, I could say visually like there, right? Oh, I went 100 more tickets sold. Guess how much more money I brought in? That would be what, $2,000. So in this case, you could have also said here, for an additional additional 100 tickets sold, what happened? You got an extra $2,000. But if you look at that number or the ratio, okay, what is actually 2,000 divided by 100? Well, that's 20, and that just happens to be, once again, the same thing, $20 per ticket. So that's what this rate of change is actually representing. Now, the last thing is calculate the horizontal intercept, also known as the X-Intercept. And how do we find that? Well, that's the Y value where the graph intersects the Y-axis. Oh, wait a minute. Horizontal. Sorry. X value. X-axis. What am I thinking? X, right? So the idea here is the dependent variable, or the Y value, is 0 in this situation. So if I look at the graph, where is it equal to 0? Where does it cross the t-axis? Right above there. And I can visualize that and say probably 50 tickets. Okay. So from the graph, the answer here is 50 tickets. Now, if I actually did this with an equation, remember my equation was P equals to 20t minus 1,000. Well, the Y value has to be 0. My profit has to be nothing. And now I'm just trying to solve this equation. 1,000 equals 20t. Divide both sides by 20. Look at that. 50 tickets. And also, if I ask you now for the vertical intercept, gave you the answer already. Yeah, that's where the Y values, where the graph intersects the Y-axis. In this case, the independent variable, or the X value, has to be equal to, that's right, in this case, it's 0. And in that case here, I'm looking at the graph, and when it's 0, boom, it's negative 1,000. So the answer from the graph is just negative $1,000. So I lost $1,000 if no tickets are sold, right? And once again, if I just were to give you this equation, I'm really saying let t equals to 0, so 20 times 0 is 0, and your profit is negative 1,000. So really, I'm saying if no tickets are sold, guess what? You lose. You lose how much? $1,000. Okay. Oh, I guess I should go back up here and do that too. Interpret the answer. Here, I'm saying I need to sell 50 tickets in order to not lose money. So the term in industry is called break even. To not lose any money at all. Okay? So there is a way where we can interpret the graphs of a linear function, use it to help us answer questions in a real life situation to hopefully make sure that you will not fail and lose a lot of money. Alright? Okay, final page. A few more things. Okay, this time, once again, we're talking about properties of linear relations. I'm giving you situations, and hopefully you can analyze them and solve. So the graph below shows the distance away from home as a function of time. Time could be 30 minutes, 30 hours, I don't know, but it's just 30. 10, 20, 30. Distance, 100 kilometers, 100 meters, don't know. But notice, it says write the coordinates of points where the graph intersects the axes. That would be this one here. The y-intercept, so 0, 100. Oops, 100, I wrote down 1,000. And another one down here on the independent axis, 20, 0. So determine the vertical and horizontal intercepts. Now, if I ask you just for the intercepts, you don't have to give me coordinates. The vertical intercept is just the value. In this case, 100. And describe what it means? Well, you begin 100, whatever, I'll just say 100 units away from home. That's what that vertical intercept means. At the initial point, at the beginning, that's how far you're away from home. The other intercept is 20, right? That's the horizontal one. And what does that represent? Well, it looks like it took 20 whatever units to actually get home. So it represents the time it took to actually get home. Okay, and if I had here, let's say the domain and range. Oh yes, domain. Those are the possible x values. In this example, it looks like my time has to be between 0 and 20. Real number, because we can have like half a second or half a minute. Range in this case. The distance also lowest is 0, highest is 100. It also has to be a real number. And there you have it. See, domain and range coming back again. But finally now, let me answer or ask this part. What is the rate of change in this scenario? And what does it mean? So that's the thing where we're looking at the change. Notice the change has to be something like this. Look, for each what? Go over 10, what happens? I go down negative 50. So really, if I look at this, I'm saying negative 50 whatever units in distance. Let me just call it meters just for sake of it. And the ratio there is going over 10. Let's leave it in time. Let's just say seconds. So the rate of change is really just a ratio here. Okay, it's a ratio of the dependent change divided by the independent change. And in this case, that is equivalent to negative 5. And like I said, in this case, it's meters per second. I made this up. Okay, you use whatever units you're actually given. But negative 5 meters per second. In this case, the rate of change of distance versus time. The rate of change of distance versus time. And for those of you taking science, perhaps you can see this, or even if you sit in a car with your mom or dad, that rate of change of distance often is called the speed, or really in this case, the velocity. That's, of course, speed with direction. Okay. All right. I guess that's it. So I've tried to show you how we can use this in different scenarios, using it to analyze the situation to give us some data to describe what's going on. I think now you're ready to do the assignment. Good luck.